Well, hello, Internet, and welcome to part 2 of my machine learning live stream series. Today, we are going to have to, I'll take the cover off my microphone. This is a live stream, so things happen. Okay, so today what we're going to focus in on is what are called binary and multi-class classifications. And I'll be doing 2 example real-world projects. In the first one, I'm going to take the chemical content or chemical information about different wines, and I am going to utilize that to then predict whether a expert on wines would rate it as a great wine or not. I'm going to do that. That's going to be a binary classification, so it's either going to be a good wine or a bad wine, you know, an either or situation. And in the second part, for multi-class classifications, I'm going to do something that's very commonly done, and I'm going to use handwritten numbers, and I'm going to create a model that is going to be able to predict those numbers by analyzing images. And thank you to everybody that is here. Looks like this is a pretty popular tutorial series, which makes me happy. Okay, so do you need, first off, what do you need to know? Well, it'd be nice if you watched part 1 first, which is on YouTube and Twitch. One thing to mention, however, is that the comments you see on the screen, those are coming from Twitch. So if you want your comments to show up, you have to go to Twitch to do that. But if you're on YouTube, I see all of your content, all of your messages as well. At least I should. Yes, there is, 77 people watching, and nobody on YouTube has commented. Anyone here? I'm just checking to see, verifying that. There you are. I'll get into all the specifics of everything as we continue in regards to how I'm going to be analyzing this. What other comments did I get? Equations. Oh, okay. So that's somewhat unrelated. Thank you for the question. I actually have a video about solving word problems on my YouTube channel, if you can find it. It's around the same time that I did algebra videos. So I did a whole entire video on nothing but solving word problems in algebra. Just a comment that I got. Okay, so what do I want to do here first? Well, I want to review, and in regards to what do you need to know to be able to do this stuff? Well, you don't really need all that much. Maybe I need to move this over a little bit. Oops, that's a little bit too much. Let's try to put this here. And I'm using Google Colab. So the question, if you have the question of, do I need to have a super powerful computer to be able to follow this tutorial? You do not. And in regards to what knowledge you need to know, it's very helpful if you understand Python. So I would say that. Hello, Daniel. Thanks for stopping by. And somebody says the Twitch quality resolution's better than YouTube. Sorry, guys. I'm just working. I'm streaming on both streaming platforms at the same time. So there's those different things. So I just want to quickly review some of the basics that I covered in the past video so that you don't necessarily need to watch it if this is all you're interested in. Okay, so when I talk about input neurons, what am I referring to? Well, I'm referring to what we call features. And they are things that are going to be used to make predictions on labels. And one of the things I like to use as an example, because it's very easy to understand, is the concept of looking at a home. So you have the number of bedrooms, the number of bathrooms, the square footage, okay? Those would be called the input neurons, so those would be called the features. Now your label would be the value of the home, and that would be your output neurons. And then in between those two things is what we call hidden layers. And what they do is they apply weightings to things like the number of bathrooms, the number of bedrooms, and the square footage to see which are most important in calculating the ultimate value of a home. So I hope the input neurons, hidden neurons, and output neurons. The hidden layers are what decides what are the most important features if our ultimate goal is to find the value of a home. So hopefully that's completely understandable. And what we're doing here is largely using numbers to predict other numbers. And basically, that comes down to tensors. And what exactly is a tensor? One of the simplest ways that I like to explain it is you need to provide your model, which is going to, use numbers to find other numbers, and needs that information to be represented in a numerical way. So for example, if you have the color of pink, so let's see here, there it is. So if you have the color of pink, maybe I'll turn these off actually, so that doesn't get in the way of anything. So everyone is equal. I see everybody's comments, but there, I got rid of some of the comments, but I'll read them as we are going. Okay, so what we're going to do here is if you have the color pink and you want to present it in a numerical way, one thing you could do is you could say that it's 100% red, it is 0.075 or 75% green, and 79% blue. Okay, so there you represented the color pink in a numerical way, and that is really simplifying a tensor, but I like to teach through code and actually working things out. Somebody asked me a question about inventory analysis. That's what I do a lot of for work. Maybe I'll get more into inventory analysis as we continue. It's a little bit more complicated. So what are we going to do here? How are we going to improve these predictions? And I'm basically covering what I did last time. Well, one thing you could do is just provide more data to your model to analyze. Another thing we could do is increase the number of hidden units, meaning, again, when I say hidden layers or hidden units and things like that, what I'm saying is increase the number of weightings to the features until we get our desired output. What else can we do? Well, we can try different activation functions. And you might say, what's an activation function? It just helps us decide what data is important in reaching our ultimate goal. Then we have optimization functions. What they're going to do is they're going to smooth our data to get to our expected results. See, all these jargon terms sound complicated, but they're not really. And then you have learning rate. And what that is defining how much you want to change the movements in your predictions, movements towards your ultimate goal, based off of any different errors. Okay, and that like if your goal value is down here and your current prediction is here, and you want to move, I'll move it up a little bit. You want to move these towards each other. Well, the learning rate is just how quickly are we going to move from this position up here to here. Okay, now if you go too far, you might go past it. So if you increase your learning rate, you're going to move quicker towards your ultimate goal, but also there's the negative that you might overshoot that goal. So hopefully that makes sense. And also you can fit longer, which just means you are increasing the number of times that you try to fit your data. And I'm going to be playing around with TensorFlow's neural network playground again to show all of this information in picture form and things like that. Okay, what do we have here? You have different hyperparameters. Basically, your hidden layers are going to be a minimum of 1 up to an unlimited, but normally we work with like 4, something in that area. Your input layers are going to be the number of features you're analyzing. And if you want to see the wine part, here's all of the data that we're going to be using for estimating our wine, whether it's white or red wine, acidity, volatile acidity, all this stuff. So yes, we're going to be able to take all this raw sort of chemical information and actually just look at that and say, this is a good wine based off of these numbers, okay? And that is going to collaborate with expert opinions. So it's pretty cool. You're turning your computer into an expert on wine. And obviously you can then, if you have similar data in any other regard, you can teach your computer to be as good as an expert at judging anything, basically. So it's pretty fascinating stuff. And this is just the tip of the iceberg of cool things we can do. Output layer with a binary classification, your output is just going to be 1. So we're going to be using Relu, which I talked about in the last video. Won't really get much into that, but I just wanted to put into table format everything that we are going to be doing, and then just jump right into code, which is what I like to do. Okay, so what are we going to need? And this is Google Colab is what I'm using. It's 100% free. And, you know, like I said, you can do this stuff on your on a junky laptop, and it'll work perfectly fine. All right, what do we need? I'm not going to go into the specifics of what NumPy and Pandas are. They just allow us to work with numerical data and provide all sorts of really awesome functions that we can use to manipulate things. Matplotlib, obviously, well, maybe not so obviously, but it's going to allow us to plot all sorts of things. Seaborn does something similar. Here's TensorFlow, which is what we're going to be using here to go and make all our predictions. And then you have scikit-learn, which is a machine learning library as well. And more specifically, TensorFlow is just a deep learning API for creating neural networks. And here it is. So let's just get right into it. You can ask me questions as I go. I'm doing very well. Thank you for stopping by and asking. I have to drink tea, otherwise I will lose my voice. Okay, so this is where I originally got all the wine data, but I went and took it and cleaned it up a little bit and threw it on my GitHub, and you can find that. Let's just, where can I even paste this? I'm going to put everything on TensorFlow, or I'm going to put everything on GitHub code-wise here or a little bit after this live stream ends. I just posted into both of the chat areas where I have all of this information. But what you're going to want to do is you're going to go over here and click on raw, and this is what you need, and you're going to copy this like that. Then you're going to jump back over into Google Colab, and we could start writing some code, which is the best way to learn. At least that's what I think. Okay, so we need to get our wine data, and to get it from a CSV file, you just go PD, that's pandas, and read CSV, and then we are going to just throw our quotes inside of here and link to our CSV file that we have on GitHub. And then we're going to go and let's say we want to get the first 5 of them just to make sure that this all works. Now I have to run everything, so let's go run. Oh, I forgot to do my imports. That's the reason why it didn't work. And a little bit slower than normal today. Google, why are you not fast? Okay, and there we go. So we see that we are able to get all of our wine data, and we're going to be manipulating all of this data. One thing that's bad here is we have white. What's that mean? We need to convert that into a numeric. Also, we need to normalize this data, because here we have like 7s and 6.3. Over here we have 0.27, 0.045. We can't deal with that. So what that means is normalizing just means we're going to put everything on the same scale. So we're going to have these values be represented between a value of 0 to 1. And that is our goal. That is what we are going to be able to do. Okay, so we got our data here. Now we can start working with it. Well, one thing that we may want to do is our data might be damaged. We might have rows that have data on it that is not, there's no values in it. So we just want to get rid of that. But what I want to do first is I want to check to see if there are any situations in which that is indeed true. So I'm going to come in and just say wine data, and I'll say is NA, and I'm going to go and get a sum for all of my different columns on any missing data that we might have. Yep. So you can see we have 0, 10, 8. There's a whole bunch of problems. Well, who cares? We can just go in here and delete those rows for any situation in which we have those problems. So wine data. Yes, this live feed will be available on Twitch as well as on YouTube after I am done. Thank you very much for I thank you for the nice comment. Okay, so what I want to do is I want to delete all of them. That's since I have a lot of data here to work with. Normally what you could do is you could it's going to damage your data, but you could do like means between different things. The mean, like if you had like one cell that was missing in one column, you could go in and do things like, well, let's just throw the mean value inside of that, but that's going to dirty up and mess up your data. So it's better to have complete data that you know you know, all the values you have are good. So I got that, and this is just going to delete everything. So then I can just come up here, and if I grab this guy right here, after I run this, paste that inside of there, and boom, and now you can see all of our data is clean. We got rid of all of those junk problems. All right, and a lot of what you're going to do in machine learning and deep learning and such, and data science in general, you're going to be cleaning data, lots and lots of cleaning data. And I have other videos on how to clean data, but we're going to cover everything, most of the common things here. Well, one thing that I'd like to do here, if we look at our data, what do we have? We have type. Well, that's not very descriptive. I would instead prefer that this column has a name, and then I also know that I want to convert all of the white wines to ones and all the red wines to zeros. Remember, everything has to be numeric data. So I'd like to come down here and rename this column. So I'm going to say wine data and rename. And you can go and rename multiple different columns. When would you replace value? Somebody asked a question. When would you replace values with the column mean? You normally wouldn't. The only way you would do that is if you, for one reason or another, thought that the mean value would be representative of your data and not damage it. Okay, there's situations in which that can be true, but it's a negative thing to do, and it's preferential to not do that. But there are circumstances in which you're like, well, the mean is going to be a good approximation. And off the top of my head, right now, I can't think of an example, even though I do it all the time. So I'm sorry about that. All right, so what we're going to do here, we only need to change one column name, but if you wanted to have multiple different column names, you would just stack these different key value pairs. So I'm going to say the column that is called type, I would prefer that it be called white wine. And like this. And another thing you need to do is you need to, if you want this change to be updated for your data frame you're working with, you have to say in place is equal to true. Then it will update the actual data. All right, and then we can come in here and do wine data like this, and you can see that it didn't work. Why didn't it work? What's going on, you? Oh yeah, it did. White wine. There you are. And so you can see this is white wine, and that's what I wanted it to be called. All right, so good. So now what I would like to do is change the actual values. Yes, I'll be covering everything. I'm going to be doing machine learning videos. I'm gonna make a new one, a live stream like this, every other week, basically for the next 6 months at least. So, and it's noon Eastern Standard Time, and of course, if you missed the video, it will be available on both platforms. You can watch it any way you want, and I'll edit them a little bit. Okay, so what do I need? I'll be covering everything you could possibly ever want to know about machine learning, because this is like what I do for a living. Okay, so what I want to do is I want to make all the white wines 1 and all of the other colors, which is only red, 0. So how can I do that? Well, I'm going to say white wine data, location, and I'm going to say wine data, and this is the column that I'm targeting. So I called it white wine, and I'm going to say if it is equal to white. Well, in that circumstance, I am going to have this be, whoops, don't mess that up. Okay, so let's go back here. Let's go. And if the value in that column is white, I'm going to give it a value of 1. All right, so we have to do white 1, and this is going to be equal to 1. All right, and then I'm going to do basically the same exact thing for my other ones. So if it is equal to red, well, in that circumstance, I'm going to give it a value of 0. And then we could come in here and we could go wine data like that. And I probably should have did head or something. You can see we have values of 1 and we have values of 0. So that's good. All right, so what do we need to do now? Well, another thing that I would like to do is I'm judging these wines, and I know nothing about wine. I don't even drink wine. I just thought this was an interesting data set that was very easily accessible, so that's why I picked it. I'm not a wine lover. I don't even drink wine. I drink green tea. Okay, so what do I want to do now? Well, I want to, as a non-wine expert, I want to judge. If you look at the data that we have right here, so why can I not cycle through it? Oh, there it is. Okay. So if we go over here, you can see that we have a quality rating. And this is what a wine expert has said, this is a good one or this is a bad one. Well, I've decided that anything over 7 would be considered a really good wine, and anything under it would be considered not a great one. All right? Just as a non-wine expert, this is my rationale for how I'm doing things. So what I want to do is I want to change those values again. So I'm going to say wine data dot location and wine data, and I'm going to say quality is the column that I'm cycling or that I'm targeting. And I'm going to say if the quality is less than or equal to 6, well, I then want to change the value in that specific row in the quality column to 0. So I'm going to say 0. And then I am also going to say that otherwise I want to say that it is a good wine. So I'm going to say if it is greater than or equal to 7, well, in that situation, I am going to say that this is a good wine. So, and then come in and say wine data like that. See, pretty understandable, I believe. And now we can come over here and look, and you can see that there are no good wines. Okay, so far there are no good wines. So you may ask yourself, well, how many good wines are there? Maybe I just completely messed up everything, and that's the reason why I'm not getting any good wines. Well, let's find out. So we can just say wine data, and I am specifically targeting quality. Again, if it's equal to 1, well, I want to sum up all of those that are equal to 1. So yeah, I got 1,271 good wines out of my total that we have here. And let's do this, and wine data. So you got 64,063 wines, and of those wines, 12,071 are good wines. I also showed you how to get the total number of samples. Okay, so now what we need to do is we need to normalize our data. And by normalizing, what we're meaning is we're converting non-numeric data into numbers. And also we are putting all of these different values on the same scale. So I want to, instead of having some values that are like 8 or 10 or 15 and other ones that are 0.025, what we're going to do is normalize them so that they all fall between 0 and 1, while at the same time preserving the original distribution of those values. And the reason we want to do this is because machine learning algorithms in general work better whenever our features, remember what features are, they're the things we're going to use to make predictions about our labels. All right. So that is what we're going, that's the reason why we want to do it. We want to make sure those are quality. So I'm just going to go CT is equal to, and we can say make column transformer is what is going to be used to normalize or ultimately normalize this data. I'm going to come down here and I'm going to go and throw this right here, and we will use min max scalar. And in the last video, I also showed how to one-hot encode data, and so that's something I covered last time. I don't think I'm going to do that this time. Anyway, you want to find out about one-hot encoding, you can check out that video. Believe me, there will be more about one-hot encoding as the tutorial series continues. Okay, so what are we going to do here? I'm going to list out all of the columns that I want to normalize. And I am bad about this stuff, so what I'm going to do is I'm going to go fixed acidity. I'm going to copy that and come down here and paste that inside of there. And we're just listing out every single column that we want to normalize. So let's get this. I thought I turned that off. Maybe I didn't. Whoops, I accidentally did something. Okay, so we're going to go fixed text acidity and volatile acidity. So let's get that and paste that inside of there. And citric acid. And copy that. Kind of just thought it was kind of cool to be able to actually make predictions like an expert based off of just using pure raw data. I mean, it's kind of neat. Okay, which one did I just get? Citric acid. And residual sugar. And we'll paste that inside of there. And let's go on to the next line here. What do we got? I am going to get chlorides. I'm going to do this for all of these guys. And chlorides. And what's the next one? Chlorides. I'm getting rid of this. Let's go here. I think it's in here. And automatically trigger code completions. There. Save. And that should keep the stuff from popping up all the time. There, you learned something else. That's a Google Colab thing. And it normally isn't a problem, but whenever you zoom in on the screen like I am doing right now, so that you can see the code that I'm typing, it's sort of, oh, it popped up again. I don't know. Okay, so total sulfur dioxide. And paste this here. And what else do we got? The density and the pH. And grab it. And paste that. And I believe this was just pH, like that. And a couple more. Get rid of that. Sulfates and alcohol. And then we're done. So we got all those different things. Boom. And alcohol. Alcohol. And that is everything. Yes, the other one is quality, and we don't need any of those other different things inside of there. So it got all those different guys inside of there, and that is going to allow us to normalize all of our data. So let's just make sure I don't have any typos. I shouldn't, since I copy and pasted everything. And this guy right here, I do not need. Just leave it there. Okay, so now what do we need to do? Well, we need to separate everything into our features and our labels. So one way that we're going to be able to do that, features, remember, all the things that are going to be used to predict ultimately our goal. So all those chemical compounds and chemical tests are going to be used, those are the features, to determine ultimately if a wine is good or not. So that is what we're going to do. So I'm just going to label this as X. This is common for people to label everything as X and Y in these circumstances. Not that it's always done this way, but it is very commonly done this way. And it doesn't like that. Okay. So what I'm going to do is I am going to say that I just want to, for all my features, I'm going to drop out the one thing I don't want, which is quality. So drop, and I'm going to drop out quality. And you say axis is equal to 1. And this is going to give us all of our features. And if you're just tuning in, all of this code eventually will be on GitHub. And I posted in both comment sections exactly where the link to all of it. Except it'll have like tons of comments. You just have to give me a little bit of time after this tutorial ends to post that. But if you're watching this on the 19th, it will be up there. Okay, and then you just want the quality data, and that is going to be our label, our specific label. And if we just want to check what exactly X looks like, we can come in and we can see that. And it's basically just got rid of quality. Everything else about it is exactly the same. Okay, so now what I want to do is split into training and test data. So how we do this is I want to get the first 80, and I'm going to use that to train my model. And then the last 20 are going to be used to test it. So we'll just say get first 80%. So how exactly are we going to do that? Well, we're just going to go length, like I showed you before, wind data, exactly like this, times, and 0.80, and that is going to be 5,170. So now what I want to do is I want to build the training and the testing data sets at the same time. So let's get this here. And how we're going to do that is we're just going to call x and train and x and test and y and train and y and test. And then we can use this awesome little function that is called train, test, and split, and pass in x are features, y are labels, and then our test size, this is what you define. I'm going to be testing my results on 20% of the data versus 80. Well, you just put in your test size in this circumstance, so that would be 0.2 for 20. And then what you do, if you want to be able to reproduce your results at some point in the future, so it's going to be random, but you want to reproduce these same exact results, well, you can come in and say random state and set this to a seed of 66 is what that, you can put any number, just use the same number and you'll get the same results in the future. Okay, so we got all that. So now what we need to do, and the reason why it's so easy for me to go in here and just list out all of these different titles is because when you're working with this type of data and trying to get these type of results, you almost always do the exact same steps in exactly the same order. So that's really awesome. Thank you very much. I'm very happy you enjoy my tutorials. Okay, so what I want to do here is I want to transform my training data. So what does that mean? I'm going to normalize it. Remember whenever we did this thing up here? Well, we're going to use this now to normalize all of our feature data. So how you do that is you go CT and fit and pass in X train like that. And then I'm going to transform the training and test data with normalization as well. So I'm going to call this normal just to separate it. So you're going to be able, I don't want to overwrite anything. I want to keep it there, but I want to give it informative variable names so that it'll be easy to figure out exactly what it is and all of the steps. And if you do this a bunch of times, you're going to realize that, you know, you do the same thing over and over again. You use a very similar type of naming convention over and over again, and then you'll be able to just do this stuff so easily. It's really amazing. Doing, you know, some of the most complex types of things without even thinking, and it's kind of fascinating. Okay, and then we throw our test data in there for that. Okay, did I spell transform wrong or something? Let me see what I did. CT transform, CT fit. Did I not run? I might not have run everything, so let's do a run all again. That's probably what I did. Don't know why it's not working. Did I get a name wrong? What is it saying here I did wrong? Was the direct cause of the following exception? A given column is not a column of the data frame. Okay. Well, that means that up here, I must have used an incorrect column name. Not sure which one of those might have worked. Interesting. Let me see here. If I can grab this out of here and maybe just copy and paste that over into this again. Okay, let's just grab all of this and paste it in. See if this works better. Okay, I'm just grabbing the column names and hopefully getting the names correct. Okay, so I got all of this and paste that inside of here. Okay, and run that. And then let's do a run all. One problem with going and doing everything 100% live is sometimes an error sneaks in. Okay, Did I type one of those incorrect? Yes, it looks like I did because everything tested out. I don't know. One of those column names I guess I copied and pasted incorrectly. Sorry about that. Okay, so what are we doing now? I am going to got that all working. Well, let's go and just take a look at what it looks like just to verify that the data has been normalized, and then you can see what normalized data looks like. See? Everything is all between the values of 0 and 1. That's what normalization means, and you can see an example of it right there. Okay, so before we proceed, I'd like to take a look at TensorFlow's playground because I think it provides a really nice way of being able to visualize what exactly we are going to be doing here. Not that, this. Okay, so, and it's just at this location, playground.tensorflow.org. Okay, and if you go here, you can see you can define what type of problems you want to work with, whether you want to work with classifications, whether you want to work with regressions. I'm going to be working with classification. It's either going to be a good one or a bad one, remember? Okay, and you can see here an example of what that type of data could look like. And what we're going to do is we're going to be able to visualize exactly what happens when we plug this information in. Now you can see I have a training set is going to be 80% right here. So that's what I defined on this guy. And you can use any of these different models. I'm just going to use this one because I don't know, it looks nice. Okay, and you can see here we're using 2 features. I'm actually going to be using a lot more than 2 features, as you saw, to judge the wine, but I'm just going to keep it like this because I think that helps. Then you have the number of hidden layers. I'm just going to keep this as 2. You could, of course, come in and increase that. Keep it simple. The activation, I'm going to be using Relu, just like I talked about previously. The learning rate I'm going to use is 0.001. And it's kind of spectacularly amazing how often the perfect learning rate is actually 0.001. But later on in the video, I'm going to show you how to calculate the perfect learning ratio. And you can see here are going to be our outputs. It's going to be either a good wine or a bad wine. Now what we're going to do here with our model is we're going to run this and we're going to test it. And you can see everything classifying our wines over here. And you can see that it is by using just this simple data, and as we are going to create our model very soon, it is going to separate the good wines versus the bad wines exactly like that. And you can see that it didn't take that many epochs to be able to come in and specifically come in and produce fantastic results. So now all we need to do is take all that awesome stuff that we just saw on the playground and build a model in exactly the same way. One thing that is often people ask questions about is what exactly do you mean in regards to ReLU and TANH and linear? Well, linear, I think everyone understands. Linear just refers to like a regression line. So that would be a line that would go through all of our data and try to provide a mean score for our data. So that is linear. It's a straight line. But what do all these other things do? Well, you see, when you look at this data here, it's not a straight line, is it? It's a weird shaped thing. Well, how exactly do you go in and actually make these weird shaped things? I'm getting a little bit in the weeds here covering this, but I want to show you exactly what is going on with these different activation functions so you can visually see exactly how we draw lines like this to encapsulate our data versus creating a linear straight line, which wouldn't make any sense with our binary data that we're working with. So I'm going to show you some real quick examples of exactly how that works. What do I want to do here? Let's do, doesn't make sense for it to be there. Let's try this, and I'm going to say text. I wasn't planning on covering this, but I'm going to cover it just because it popped into my head, and I think it makes a lot of sense to be able to do this. Okay, so what do I want to call this? Let's just call it activations, just to keep it simple. So I'm going to come in and activations. Okay, create that. And then after this, I'm going to go and create some examples where you can actually visually see exactly what is going on with these different things and how they are able to take move away from the world of linearity and straight lines into the world of creating these like bounding boxes of any shape or size. Okay, so I'm going to create just a sample tensor, and I'll say TF and cast TF dot range, and let's say that I want values between -15 to +15, and this is going to be a 32-bit float. And this is the old world where we only could work with linear data, okay? So here's our linear data, and it's boring. It's a straight line, and you could just imagine that there's dots up here, and there's dots down here, and this line was created by taking these dots and moving them towards the center, and that is how we create that sort of boring thing. Okay, so why would we then come in and work with these other different options if, you know, or how could we not? Well, let's first take a look at Relu and exactly what Relu does. Okay, so this is going to be Relu, and there it is, and this is Python, I hope. Okay, let's create a function for it. So we'll say Relu and x, and what does Relu do? Well, all Relu does is it turns all negative values to 0, and otherwise all the positive values are left as they are. Okay, so I'm going to create it, and there is a simple function in TensorFlow that does exactly that. It's called maximum, and I'm going to say that it gets passed a value, which is going to be x, and it's either going to provide a 0 or it is going to provide an x. If you look up the documentation on Relu, this is exactly what it tells you to do. You could actually do that. You could come in and you could say TensorFlow Relu. There we are. Okay, TensorFlow Relu. There it is, and boom. And I don't know why it's doing that. Okay, and so you can see, look, max features. See? There we are. All the stuff that you would want. And you can just type in that for any of these different activation functions, and they'll give you the exact algorithm that is used for working with this data. So I'm going to say that I want to plot this, and now you're going to see the first situation in which we are going to, on a very simplified way, work with linear data. Okay, so there's Relu, and look at that. Now we're not working with linear data anymore. Look at now we have this bend. Well, now we're going to introduce even more, because we're going to be able to work with even other additional functions. So we also saw Sigmoid. We were working with that. You might say, well, what does Sigmoid do? Well, Sigmoid allows us to take and actually do curved lines. And I'll do a really elementary example here. So let's just call this Sigmoid. Yes. Hello, Miko. Thanks for stopping by. Okay, so here's Sigmoid. Feel free to ask any questions that you might have. If you look up Sigmoid to find out what exactly it does, it's going to give you this formula. So type in TensorFlow Sigmoid, and it gives you this formula, and then you can type it in yourself, or you can just take what I just give you right here. You can trust that I know what I'm talking about, and I'm giving you the right formula. So -x, this is what Sigmoid does. And then we can come in, and we can actually plot Sigmoid, and I'll show you tangent after this. So sample tensor, plot it. Oops, what I type in? Wrong. Plot Sigmoid. Oh, okay. I just hit the wrong little. Forgot to put a parenthesis inside of there. Sorry about that. Boom. See? Now we can do curved lines. Okay, so we can break on angles using Relu on sharp sort of angles, and then Sigmoid allows us to come in and do curves around our data. And then tan H, that was the other one, and I'll show you exactly what it allows us to do. Let's define another function, and we will receive our tensor again, and I am going to just return this, and pretty simple, isn't it? I'm just using that function, and and then I can come in and plot this. So I'll just say plot and this and sample tensor. got all that right. And now what you're going to see is it's sort of in between Sigmoid and Relu. It's sort of making these mini linear lines and sort of going around angles in that way. And if you combine all those different types of ways of drawing the different graphs, then you're able to estimate the examples that we see exactly right here. All right? So hopefully now you have a really good understanding in your brain. I can't stream every week. Every other week. Sorry, June the 1st is the next one. I've been really busy at work lately, and that's the only thing I can guarantee you every other week that I can make a video like this. What else can we do here? And okay, I guess we can just build the model. All right, build the model because that's what we're going to do. All right, and a lot of this is going to be very similar to what we did previously. So the very first thing we want to do, if we want to be able to reproduce our results in the future, we need to generate a random seed. So to do that, we say tf and random and set seed. And I'm just using 66. There's no reason why I'm using 66 other than I just decided I liked 66. Okay, very first thing we need to do is create our model. So I'm just going to call this model1 is equal to tf and caras and sequential. And basically, we're just going to define a whole bunch of different activation functions here, which I have said before is just going to help our network decide which data is the most important when trying to properly guess at a label. And our labels are going to be, is it a good one or is it a bad one? And like I said before, they receive the data, they add weightings to it, and then they pass their results onto other hidden layers that, again, just add activations and biases. And I'm going to get more into the model after I do this, exactly what's going on with the model. But that's the basics of it. And probably immediately after I create this model, I'll actually explain each part here step by step and exactly what is going on with these different guys. I don't want to be all the way over here. Let's just go over here. I need some space. So I'm going to say tf and caras dot layers. So you should be an expert. If you watch all this, maybe not an expert, but you should understand the vast majority of jargon that you're ever going to see. And of course the jargon just continues each time, but I don't think the jargon's hard to understand. Just applying weightings to things. Caras activations like this. And what I said before, well, in our example, is we used Relu to be able to, that's our chosen activation. And remember, from using the playground interface, that's exactly what the activation is used right here. All we're doing right now is writing the code to completely recreate exactly what you see right here. Except we have more features. Other than that, and we're also going to have 3 hidden layers. But other than that, it's exactly the same. Okay, so we're going to do basically the same thing, and I'll explain what each of these individual layers is doing and how they're referring to each other after this is over. And, you know, after I go and start doing some calculation. Okay, and then this final is going to be our output layer. So we're either going to get kicked out one value or another. It's either going to be a good one or it's going to be a bad one. That's what the 1 represents there. Okay, so now what do we need to do? Well, we need to compile our model. What does compiling our model mean? It means that we are going to calculate errors, we are going to optimize, and then we're going to evaluate, and we're going to calculate errors, optimize, and evaluate over and over again. You're going to hear people refer to things as loss. Hello, nice to see you, Earl George. Why did you use the number of hidden layers? It's just, it's going to change depending upon what type of data you're going to work with. Sometimes you can play with you can use multiple different neurons, you can use multiple different layers, but in most simple applications like I'm using right here, and even in rather complex models that you'll be working with, you don't need a ton of layers. Okay. I'm going to refer to loss. What's that mean? That is the average of errors between your predictions and the actual observed data. And that's what loss means. I am going to also, let's just go in here and actually compile this. So model 1 dot compile loss tf dot caras. So losses. Remember, it's just the difference between what your model believes is true and the actual real world results. So cost entropy is what we're going to use in this situation, and the binary is you're basically just saying, hey, this is going to be an either or situation that we're going to be calculating. Then we're going to be defining what optimizer we're going to use. It's optimizer. Yeah, optimizers. It's optimizer. And what we're going to be using is Atom. And Atom is also where you can define your learning rate, but the default learning rate is 0.001, and I'm going to show you in a little bit later exactly how to calculate your learning rate very, very accurately. This is why I get confused. See, this is optimizers, but this is just optimizer. Obviously, there's multiple different optimizers, and that's the reason why it does that. This is where you would type in your learning rate, but I'm just going to leave it as the default, and then maybe we will come back and change that. And the metrics in this situation, I want to test the accuracy of the model. So I'm going to define my metrics, if I can spell metrics the proper way. So METRICS. Oh, that's right. It's just giving me an error for some weird reason. I'm going to say that accuracy is what is important, and that's the data that I want to be able to pull out. It's giving me a weird squiggle for some reason. I don't know why. Okay, so now after we do that, what we want to do is we need to fit our model. So we're going to take the data and basically try to fit the data, and I'm probably going to use 100 epochs or 100 tries. And and just an epoch is just a full iteration over our training data. So again, jargon that I don't think is that big of a deal. So, there we are. Very common to label this as history, and then we're going to be using history to analyze all this data. I'm going to say fit, and I'm going to say x train and normal, and y train, and I said that I want to use 100 epochs or 100 tries to train this data. And this is going to calculate it. And there you can see it is. All right, and while it is doing that, I'm going to run upstairs, get myself some more tea, and I will be back in a minute. All right, I'm back. Okay, so got my tea. So good. Okay, so what do we got here? Everything worked out good, so that's good. And this takes, I don't know, about a minute or something like that. That's why I thought it would be a good time to take a little bit of a break here. Okay, so we fit our model, and basically what is going on is the features are going to be passed, and then they're going to be converted. I'll get more into the specifics of this and exactly what is going on as it's passing through these layers. But somebody asked a question about why do I have 4 inside of here? Well, the feature is going to be passed, and then they're going to be converted into a 4-value vector. And then that vector is then turned into an additional optimized vector, okay? And then finally, we're going to convert into whether it is a good one or a bad one. But what we want to do here is after we fit all this, we want to come in and we want to actually evaluate what we did. Thank you very much for the kind comments. Do you think you can use TensorFlow to predict stock prices? Believe me, I am going to do that. Yes, I am going to definitely, that is something I'm going to do. I know a guy who's like a super genius in regards to the technical side of stock analysis. And he has some ideas. So yeah, that's something I'm going to do at some point in the future. Okay, so let's evaluate what is going on here and whether we are doing a good job or not. So I'm going to say X train and normal and Y train. And evaluate this. And we can see here that we have an accuracy based off of these bizarro chemical compound analysis. We are accurate to almost 82% on whether something is a good wine or not. So basically what we just created here is just doing this simple work is that the odds that we can recreate those chemical calculations or whatever, those chemical changes are going to provide an 82% chance that somebody's going to drink that wine and then rate it as a 7 or above in quality. Okay, so my model is almost a wine expert. I mean, it's probably about as close as anybody could be. So what it's going to come down to is exactly how can we now proceed and actually improve our model to even better results. Well, one thing we can do is we can get more data. That's always a positive. We can increase the number of hidden units. That just means we can add more weighting to get to our desired output to increase our accuracy. The one problem is if you try to overanalyze, what you do is you get something called overfitting, where the model will very precisely model the training data, but then make very bad predictions when it gets to the testing data. And in my Discord, I've had a couple people have that problem, is they actually overfit their data. So there's positives and negatives to training too much. Another thing we could do, we could try different activation functions. And if you don't remember, they're just going to help us decide what data is most important. We can try different optimization functions, and those are just going to optimize or smooth our data to get our expected results. We can increase our learning rate, which I'm going to get into learning rate here in a minute and explain exactly. Remember, learning rate is just how quickly we move towards our desired result. Now, if we increase our learning rate, that means we're going to get to our expected or the result that we want, but we could also overshoot it and go past. Okay, so there's positives and negatives to increasing learning rate, and we could also fit longer, as you saw we did here, where we had 1,045 epochs, and you saw the results just playing around here with how that benefits and not. You could go on the TensorFlow playground and play around with these different things and in a visual way see how they work out, okay? One thing I like to do is create a correlation matrix to see what data is going to, this is another thing, is to see which data points actually contribute most to whether a wine is a high quality or not a high quality wine. So I'm going to come in here and plot a correlation matrix. So let's go and define our figure size as like 30 in width, 20 in height. And then I'm going to use Seaborn here to create what is called a heat map. This is a correlation matrix. I'll explain exactly what I mean by correlation if you don't know what that means as soon as I'm done with this. And then you go absolute like this. And yes, I want the annotation to show up because otherwise you won't be able to see what it is. Okay, so let's do that. Oops, figure size is not defined. Oh, this is fig size equals. Whoops, equals. And run it. Fig size. 30, 20, why is it not working? Oh, name WIME data. Okay, so it's a different error. I just have an uppercase D inside of there. Let's go get rid of that and run it again. And another error. What did I do? Oh, absolute. Too much talking and leads to errors. Okay. This is going to create a correlation matrix, which you can't really see all that wonderful here. But you can see down here we have quality, and that is really what we care most about. So what we want to do, I don't know if you can really see this. These numbers are kind of small, but as you can see, I can only zoom in so much. But you can see that, do these numbers on their own really correlate? What's correlation mean? I'll explain it very briefly. Let's say that you have a company that makes candy. Now, if the price of the price of sugar, if 50% of what you're selling is sugar, well, if the price of sugar goes up, that is going to increase the cost for you to make said candy. So that means that the price of your candy is highly correlated to sugar. Now, hopefully there's no lead in your candy. So the price of lead would be a non-correlated with the price of your candy. Okay? So if one thing changes the results of another thing, we say it's correlated. If it has no bearing on the changes, then it is not. Hello, Alex. So there you go. All right, so are any of these highly correlated? Not really, which is really amazing that our model did so well, because the most highly correlated thing is alcohol content and density. And they're not even at 50%, and most of these other ones are single digits for the most part. So let's come in and, we could come in and try playing around with trying to make judgments just based off of alcohol content and density. And this is something you could do on your own. Chlorides and maybe volatile acidity. And you could go and instead model based off of just those limited numbers and then see if that improves your result. But what I'd like to do is plot our loss curve. We're already at 82%, which is pretty fantastic. So I'm going to plot this. So how do I plot it? I just go PD and data frame and history, which is what is provided whenever we fit our model. And I'll say history, if I can, history. Let's go in here and do this the right way. History. And then we will do a plot on that. So dot and plot. And let's go and give it a title just so it's a little bit more descriptive. And I will just say model 1 loss curve. Whoops, curve. And there you can see. So here is our loss, and here is our accuracy. And of course, we want our loss to go down, and we want our accuracy to increase. And you can see there exactly how that looks. So what I want to do now is I showed you an additional way of finding the ideal learning rate last time, and I'm going to show you a new way this time. What do you mean? Somebody says lead is not supposed to be in candy. I hope you're joking. Okay. All right. So what I'm going to do is I'm going to use a callback here to go and find my ideal learning rate. I'm going to be doing a lot of the same stuff that I did previously. So I'm just going to come up here because I'm creating a new model and I'm basically going to be doing the same things. So let's just come up here and let's copy this. And then let's come down here. I don't want to accidentally hit return and do all that over again because that would be bad. Okay, so we'll come in and we will paste this inside of here. So we're going to use the same thing. We're going to use the same activations, the same number of layers. We're going to compile in exactly the same way. Another thing you can do here is you can very often replace things like this with things like this. All right, you can look that up in the TensorFlow API and such. We're going to keep accuracy, and then we're going to create a callback, which is going to be different. Now, basically, a callback is going to work during your model training, and what it's going to do is at each epoch or try, if we change the learning rate, we're going to constantly change our learning rate, and we're going to use something called the scheduler that is going to say each time through Adam, I want you to increase the overall learning rate. And we're going to start with a learning rate that is going to be at 0.0001. And after each epoch, we're going to increase that value. And then by doing so, we're going to be able to see which learning rate is the best. So we need that scheduler that I just mentioned. So scheduler is going to be TF and Keras and callbacks and learning rate scheduler, and then I need to define exactly how much I want to increase this. So let's come in, let's say lambda. And this is just going to allow us to go and make these changes to our learning rate each time. So this is a common thing that is just common values that are often used to do this. So there's no magic in it other than, yes, this is what is commonly done. Epoch divided by 20. Like that. Okay. And then after this, we can come in and I want to change history a little bit here. So I'm going to call this history, and I'll just change this to history learning rate just to keep it simple. And I'm also going to change this to model 2 just so that we can keep all of our work that we did before and not lose it. I don't have that anywhere else, do I? No, I do not. So we'll put that there. And X train normal, Y train, and the epochs is going to be equal to 100, just like before. And this is where we're going to do our callbacks, which is just going to call our scheduler, which is just going to say, hey, increase the value of the scheduler. It's going to increase the value of the learning rate. Okay, and we can run this. If I didn't get any code, oh, I got something wrong. Let's drink something here. Epoch scheduler. Did I spell scheduler wrong? Yes, I did. Scheduler. Schedule. Let's just copy this. Oh, it's just an A. All right. Scheduler. And run it. And there it goes. And it's working. And you can see it's increasing the value of the learning rate as it continues. Okay? And it's going through and making all those calculations. And as you can see, it's pretty quick. This heat map in the basketball data, really good project, which are overpaid. I've been trying to put, but my math is wrong. Yeah, with the NBA data analysis, you quickly see that yes, there are the highest paid players are most definitely overpaid. And I don't know the specifics of why that is. Maybe it has to be that way in the NBA. I don't know. I'm not an expert on sports either, so I don't even watch sports. So there's that. But I have to pull the data from somewhere, and there we are. Okay, so now what I want to do, isn't it common to decrease the learning rate? Well, I'm starting off at 0.00, what is it? I'm starting off at a very low rate. So learning rate, and then I am increasing it. So I'm starting off very low, and I'm going well past where I know that it would be a good learning rate. Okay. So now what I want to do is I want to plot our learning rate versus our loss, and that is going to show me very easily or very quickly what is an ideal learning rate. So we'll go LRS is equal to, I'm basically just going to plug in exactly the same thing that I did previously. And times, and this will be 10 times TF and range 100 divided by 20. And then I can just, after I do that, I can just come in here and plot out everything. So let's go figure size is equal to, and let's try 2010 so it's not quite so big. Maybe I'll increase that. And then we're going to put this on a log scale. So that's log x. And we just plug in our x value, which is our learning rate. And then we can go and get our other model's learning rate here. And we can specifically get the loss on each of these. Okay. And let's throw some labels on it. So we'll say X label is going to be learning rate, and also the Y label is going to be just loss. And then if we want to also throw a title on this, title, we can throw a title on it. And this is going to be learning rate versus loss. And if I typed everything in right, that will print. And there it is, okay? Oh, that's kind of crazy. Okay, well, as we can see here, that was a little bit weird, actually. Make sure I got everything right here, because that doesn't look quite right. 10 times CF, range 100 to 20, and just verify that I got all of this in here the right way, because it looks a little bit weird. You got this, and aha, it is incorrect. Boom. And yeah, I went and increased that way too much. Okay, so we're gonna have to run it again, which means I get to drink tea again, which is a good thing sometimes. Is this just for the illustration? No, I'm actually trying to find the ideal learning rate. I just made an error. The learning rate didn't look right to me, and sure enough, it wasn't. After you look at enough of this stuff, you can just look at the plots and you know that you made an error somewhere. It doesn't have to tell you made an error. You'll look at it and be like, that doesn't look right. And then sure enough, it isn't. As you will see. Okay. Are you done? Okay. Still spinning. Okay, there we are. Now let's plot it. Yeah, that looks much better. That looks like what it's supposed to be. Okay, so after we go and we do this, that is, maybe the size is a little bit wonky, but this is basically what we're looking for. And we can actually see, okay, it's falling, it's falling, it's falling, and then we get to our lowest point, and guess what? It's at 0.001 is our ideal learning rate. We want to try to get around our lowest point. And it's actually probably a little bit over here because it's normally 10% past its lowest point. So if its lowest point is probably just eyeballing it here, looks like it's right around here or here. So 10% less, I'm just going to say that it's 0.001. And guess what? Maybe I'm wrong. I'm still learning about machine learning. Optimal rate will change as you train. The ideal learning rate is going to all we're doing with learning rate here is we're trying to figure out how quickly to move towards our ultimate result, and it's a fixed thing. It doesn't change. The only reason why I change the learning rate is to try to find this, to be able to plot this out. and I'm looking for where does this plot hit its lowest point without going up. And I think it's right around here. And guess what? What you do is you try to find its lowest point, take 10% approximately from that, since this is a log scale. So this is actually, this is going to be 0.002, and then 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is a log scale. And so if it's the lowest point is here and I want to do like 10% less, guess what? It's almost exactly 0.001. And guess what? 0.001 is the default learning rate whenever you're working with Atom. So we don't need to change anything. And so that's it. So now the only thing for us to do is to evaluate our test data, and then I'm going to explain exactly what's going on when we're creating this model, which is what I've been promising to do for a while. Okay, so I'm going to evaluate, and then I'm going to explain the model and exactly what is going on with it. So let's go and let's get our loss and our accuracy. And we can just use model 1 because model 1 used 0.001 for doing its analysis. And model 2 is messed up because we're doing all those weird, changing the learning rate. So we're going to stick with model 1. We're probably pretty happy with it. It's 82% accurate, and then we're going to come in here and test it for a couple other different things. So let's go test normal, and it's y-test. And then we can just print out this data. So we can say something like, whoops, model, loss, and this is going to be for our test set, whoops, set. And let's go and throw it in here. So there's our loss, and then we'll do the same thing for our accuracy. So plug that there. And this is going to be our model accuracy. And this is going to be accuracy. And if we run that, indentation error. Well, whoops, actually. Forgot to put that there. Why is this all indented? I have no idea. Let's get rid of that and get rid of this. There we are. And we can see here that our model's accuracy with our test data, this is data that it's never even seen, is over 80%. So pretty good. And we could come in and actually go and see, okay, was this manually check against all of this? But this, and you already know, I've already explained to you how to increase the accuracy, and that's what you can do for homework. You can go in and you can increase the number of epochs. You can go and, well, changing learning rate isn't going to do anything. You could increase the number of hidden layers, and that's just something for you to play with after you're done here so that you understand it. Okay, so we get back now to actually understanding what the model is doing each step of the way. Now, each hidden layer is going to try to find patterns, and then it's going to feed those results to our next layer. So what I want to do is actually plot out all of these different layers and then walk you step by step through exactly what is going on with them. We need another, I don't know if this is in my imports up top, but if it isn't, I'm going to just, rather than going up there and looking, I'm just going to put it in here because it's not going to hurt anything. So let's go and plot our model, and you just call plot and model like this, and throw in, well, this will be model 1, and then show shapes. This is going to make little boxes around everything, make it look nice, and that's a capital this, and you're going to be able to see our model. So here is the whole entire model. We're going to be getting 11 features passed to it, and it is going to be creating a vector of 4 for each of those, and again doing it again. And what it's doing each step of the time is trying to weight everything and add biases as well. Can somebody explain how to find it? Oh, okay. Sorry about that. All right. Okay, so this is our model represented in like a picture type of format. So what we'd like to do now is actually get an idea of what these different weights and biases look like. And you can do that by going weights and biases is equal to, and I'll say model 1, layers, and I'll just get the first here, and I'll say that I want to get my weights. And then I'm going to output this weights, and you're going to also see the number of shapes and how they're going to match up with exactly what I just showed you before. So namer, oh, I just forgot to put a comma inside of there. There we are. Here we are. So here is an example how we are going to go through here. And this guy right here, remember I said it's going to create 4 tensors for each of those features? Well, you can see that is exactly what it is doing. And actually, whenever it first starts weighting your data, it is going to start off by using random numbers. And you can see it's 4 by 4 down here. And it's going to adjust then after first creating the random weightings to decide how to best use those values to influence the neural network's decisions to get the results that we're looking for. And whatever. So let's look at our biases as well. Biases and biases shape. And, oh no, there's no, there we are. Boom. All right, and there are our biases as well. And basically, there's going to be one bias vector for each of the hidden units in a neural network. And it's going to be paired with our weight tensor. And the bias tensor is basically going to be responsible for defining how much the patterns in the weights tensor should influence the next layer that you work with. Okay? Wow, that's a lot of stuff. So that is binary classification. And now what we're going to do is talk about multi-class classification. So we just created and if you go in there and mess around with the layers, mess around with the number of epochs, you're going to be able to increase your accuracy as well. Which is just spectacular if you think, you know, just that little bit of work, and we just created a computer that can make ridiculously awesome predictions in regards to whether a wine is good or not, even though the computer obviously doesn't know what it is. Okay. Now, with multi-class classification, what that means is we are using more than two classes. So previously, it was an either-or situation. It was either a good wine or it's a bad wine. Now it's either going to be a number, handwritten number between 0 and 9. And these are all going to be images. And we're going to use a TensorFlow handwritten digit database. There's 60,000 training examples, and there's a test set of 10,000. And there's going to be 28 by 28 images, pixel-wise. And we're going to associate those with 10 different classes or labels. Okay. So we need to download the data and then split it into training and test data. This is actually really good, really easy to do because this work is already done for us because it is a data set provided by TensorFlow. So we just go tf dot Kara's data sets and mnest, and to go and get our training data and our testing data, we can just go, I'm just going to go call this the same thing because I always do. So y train. Why did I pick 4 tensors? It's just a common thing that I do. And it's just very, very common to do that. And you can try messing around with other different values and see if it improves your results, which is what all this stuff's about. It's experimenting. So I'm also going to get our test data and y. And you can't always do this, but you can do this with the TensorFlow provided data sets, I think always, because everything's split into test data and training data for you. And we can just say load data like that. I think I did it right. Yep, downloading data. And if you want to come in and actually see what one of these images looks like, you can just go plot. I showed you this in the last video whenever we were looking at images. So here's an image show and X train. Let's just get the very first one. And let's go and let's make it grayscale. Just like that. And then you just say plot and show like that. And there it is. So this is what we're working with. This thing right here, we're going to train our model to be able to come in and tell you what number this is. And you can see it's very, very sloppy. So what do we need to do? Is there anybody out there who can make a prediction? Would somebody actually participate in this live course? All right, what did I do? I downloaded my data and I viewed it and I split it into training and test data sets. What is the next thing? Well, we are going to normalize it. And how we normalize it is we just go xtrain is equal to tf and charas utils. I'm showing you multiple different ways to normalize, showing you multiple different ways to split into test and training data. I love showing multiple different ways of doing things. And some things are like, oh yeah, this is the way you do it. And other things are like, do it either way, it doesn't matter. Okay, so normalize, and this is of course going to be test and run it. Axes is equal to 1. And axes is equal to 1. Boom. All right. Cool. Okay. So now what I want to do is I want to come in. Thank you very much. We can divide pixels by 255. These are 28 by 28 pixels. Not sure what your question means. Okay, so what I'd like to do here before I proceed is to actually see how many unique labels I have in this NumPy array. Oh, no. TensorFlow is used for anything. I just showed how I could take a bunch of chemical analyses, you know, just a whole bunch of numbers and highly accurately predict whether a wine would be classified or good or not from a wine expert. You can use TensorFlow to do literally almost anything you can possibly imagine. I mean, I'm just, you know, this is just the beginning of what we're working with. Okay, so if you want to find out, it's not just image classification. It's infinitely, you can have TensorFlow do almost anything you can imagine. If you can provide the data and what, you know, the numbers, and then they somehow influence an outside number, then TensorFlow can make predictions about it. And this goes beyond anything else. I mean, you can create a chess engine that can play chess. You can create models that can play video games like an expert. You could create anything. This is all. The options are absolutely amazing. Yeah. Oh, I understand. You just got on. Okay, so let's just come in. Yeah, the world is your oyster if you master machine learning and deep learning. Okay, so these are all the possible values for all of our images. So the numbers 0 through 9. And what I want to do is I actually want to store these different label names because I'm going to refer to them later. So I'm going to call this label names is equal to np.unique and y test, exactly like I just did before. And this is just here for informational purposes. This is just the hyperparameters and some data in regards to how many hidden layers you'll have, how many neurons you'll be working with, how many output layers. So it's either going to be a 0 through 9. So that's 1 per class. Using Relu again, we're going to use a different activation this time. We're using softmax. Instead of binary cross entropy, we're going to be using categorical. And in regards to the optimizer you're going to be using, you're either going to be using stochastic, gradient descent, or you're going to be using atom. Okay, now we just build our model again. It's kind of amazing. If you do this 10 times, you'll probably memorize all of it. It's just that easy. You do the same thing over and over again. So let's do set seed, and I'm just using 66 because I don't know. It's just a thing that I've always done, and I don't know why I picked 66. Maybe it's important to somebody somewhere in the universe. Okay, so model 3. I'm just going to, guess what? I'm going to use sequential again. So Kara's sequential. Just make sure I spell sequential correctly. Oh, yeah, I did. Double guessing myself here. All right, so we'll go sequential. I'm going to move this back over here and define everything. So I'm going to say tf dot Kara's dot. Oh, one thing that's weird about this is going to be 28 by 28 pixels. What I want to do is I need to flatten those down into one tensor. Yes. And to do that, I need to call a function. Guess what? It's called flatten. So that's going to, instead of having it be 28 by 28, it's going to be 28 times 28, which I think is like 780 something. So there. Trying to do math in my head while I do a live stream with multiple different on YouTube and Twitch and doing all this other stuff. So 784, something like that. Okay, 28. Somebody out there who is not trying to do 50 things at once can tell me if my math is correct. Otherwise, I will check it. So I'm going to say, here's layers. Is 28 times 28 784? I don't know. You can tell me. So 4 and activation is going to be, we're going to use Relu again. And nobody told me if 28 times 28 is 784. I'm going to do it myself then. Let's see. Calculator. 28 times 28 is equal to, look at that, 784. Yes, who needs a calculator when you have a brain? Whoops. Thank you very much for following. Greatly appreciate that. Okay, so we're going to do this again, and we'll create another layer. So this is normally what I normally start off with. And then what are we going to do at the end? Can anybody tell me what this number is going to be? Anybody? It's not going to be 4. It's not going to be 1. It's going to be 10. We have 10 different values that we are potentially working with here. All right. And then I need to compile this model. So let's say I did call it, yeah, it's called model 3. So model 3 dot and compile, and loss is equal to tf Kara's dot losses. And in this situation, 10. There you go. 10 came back. Oh, maybe there was a delay or something. I did answer pretty quickly. So in this situation, as we saw up here, we are going to be, didn't I put it in? No, I didn't. Okay, we're going to be using, what happens is you're going to use sparse categorical entropy if your data isn't normalized or one-hot encoded. And in this situation, it is not. So we're just going to use that. So categorical, sparse categorical, cross entropy. I'm used to you having code completion be on here, but is it E? I'm not sure. I think it's a lowercase. So sparse categorical cross entropy. And after this, you can see everything, right? Yes. All right. So optimizer. Optimizer is TF, Kara's, and optimizers. There's multiple different optimizers. And I'm just going to stick with the default learning rate of 0.001. And as you're going to see, as you do more and more of these, very often that ends up being the learning rate that it ends up being the most accurate. Or is very close to being the most accurate. Okay, so there it's compiled. And I'm going to overwrite my history because that's all right. And we'll do model 3. And we just need to fit our data. So I'll say X and train and Y, train, and epochs. Let's just do 10. See what happens. Well, 19? No. 10. And might take that up. And then I am going to go and validate it versus the test data as I go and create this model at the same time. If you want to do that, you can go validation. Sort of speeds up the process a little bit sometimes. Sometimes it slows it down also. So, whoops. Got ahead of myself here. Validation data, Y, and test. And let's try it. And while I do this, yep, I'm going to go run and get myself some tea. So I'll be back again in like 2 minutes. All right, I'm back. Something really weird happened. I have more people following me on Twitch, watching this video on Twitch right now than YouTube, which I never thought that would happen. Somebody said that the resolution was. Thank you very much for following. That the resolution was slightly better on Twitch, or better. I don't know. I'll have to check on that. Using exactly the same settings for both. I have no idea why that is the way it is. Okay, so we can see our loss here. We can see our accuracy. And we are also seeing how it is working out for our test data as well, which is basically right in line. So what we want to do now is we want to find our ideal learning rate like we did previously. Guess what? We're going to do basically the same exact thing. Why don't we just go and copy and paste some stuff to speed up this whole process. So I'm going to go and copy this. Thank you very much. LV2LRN. Let's just go and paste this in here. All right, and let's change these to model 4, just so we don't mess up anything. And then we're going to test to see how everything is working for us. So what do we need to change here? No, not much. I actually see an error I made in this. So let's come up here. This, if you remember, I made an error. Remember what I said up here that in output activation to use softmax? Guess what? I didn't use softmax. So this is model 3. So this, instead of Relu, should be softmax. See, you should have told me that. All right, so anything else I made an error on? Not that I can tell. This is very, very quick. So I think I'm just going to run this again. And we'll see. All right, so there's something. When I make an error, then hopefully you don't make that error in the future. We are. Oh, look at that. Our accuracy is considerably better. I was thinking that accuracy looks terrible. Okay, look at that. Right out of the gates, our accuracy is up to 80%. And if we move it over here, look at that. 82% with our test data. Well, that's considerably better, isn't it? And that was only using 10 epochs. And 84% accuracy. 85% accuracy. And we could still take this up more and more and more. Let's see. Let's do another couple of epochs. We got some time. We're sitting here doing this. So there's 10, and I got up to 85% accuracy. And that didn't take very long, did it? Let's take it to 20. Do it again. And let's see how our results change. They should get better. Okay. So we start off at 56, 75. And there's no point in me talking. You can see. Yeah, you can see that. So let's try to get more accurate. Well, we got to 85 before. And let's see if we can get even better. So now we're able to recognize handwritten letters. And no, TensorFlow isn't only used for image recognition. It's used for basically any circumstance in which you have a whole lot of data and you want to be able to make predictions on that data. Okay, so 84, 84, 74. And as you can see, as we increase the number of epochs in this specific circumstance, it is getting more accurate. And is it getting more accurate? This is the test data over here. You can see that, right? The test data is over here. And the training data is right here. Yep, look, it's getting more and more accurate. 85%, 86% accuracy. And on your own, you could go and try increasing the epochs even more. So what do we got? 85. Well, looks like it's sort of stuck in the 86% accuracy range, which is ridiculously good. All right. And in the next video, I'm going to do even more with image recognition. I haven't really decided yet what I'm going to do. And that'll be on June the 1st at noon Eastern Standard Time, just like we did before. Okay, so what did I say we're going to do here? Whoops. We want to find our ideal learning rate. And how did we do that? Well, first off, let's make this softmax. So softmax, like that. Everything else is exactly the same. We're using sparse categorical cross entropy. The reason we're doing that is it has all the data has not been used it when the data hasn't been normalized. And atom accuracy, obviously the atom is not going to be changed because we're trying to find the learning rate. And we're going to do the same thing with the scheduler, so I'm just going to copy that. So let's come up here, so I don't have to type it all out again. You don't have to watch me type it out again. So I think if you went through this whole thing, I think you should have a really good grasp on exactly what all this jargon means. I mean, it's a lot of jargon, but I think you should understand all of it. And that's the point of every one of these videos, is I'm taking all the individual parts of understanding machine learning, and I'm sort of almost creating a learn-in-one video for each one of them. Now, it's good to go through and watch each of them, but at least at this point, you don't necessarily have to. So let's go and get this. I'm going to copy that. I'm going to paste it here. And then for this one, let's keep our epochs at 20. Validation is perfectly fine as well. We can also keep that inside of there. And then we're just going to put callback scheduler to go and increase the learning rate as we learn. And the whole goal is to be able to find an ideal learning rate by starting very, very low and working our way high. You actually don't need to go this high ever, but whatever. Okay, so this is, I don't want to mess this up. Okay, so we did that, and oops, you know what? I did mess it up, didn't I? Let's go. You know what? It doesn't really matter. So let's just leave that there. I wanted to put it down here. Well, maybe I will just copy and paste it so I don't mess this up, so that whenever I put it on GitHub, it will all make sense. So let's come down here and let's paste it right here like that. And this guy up here, I'm just going to come in and I'm going to undo everything that I did. So that's fine. And what else did I change? Yeah, I don't need the scheduler, but softmax I do need. So I'm just going to leave softmax the way that it is. And I'm going to make this 3, and everything else is fine. All right, so then let's make this 4 and 4 and 4. And then we will go and find that. Hopefully there's no typos. Okay, it's going through and doing all that, and then I can drink some more tea. There is an infinite amount of machine learning videos coming. I will, please leave any requests that you have, and I will cover everything. I'm basically just going to make machine learning videos for the next 6 months. Every other week, there'll be a new one. And I'll get into the specifics. I'll get into tuning. I'm going to get into all the different major areas and provide an example for just about everything you could ever want to do machine learning-wise. I'm probably going to even cover TensorFlow Lite. You could take these models and export them and utilize them in Internet of Things type of applications. I'm going to do that as well. If you have a question, the dude in the picture, you just ask me. It's basically, it does everything for you. It comes down to just understanding what all the jargon terms mean. But I think I did a pretty good job of explaining all of them. All we're doing is taking numbers and turning them into other numbers, and we're applying certain weightings to the numbers that go into the system. And when I say weightings, how important they are to getting expected results in the end. And that's what we're doing. It's basically like a regression, except as you saw previously we're not doing simple line regressions like in our wine example. Is it a good wine? Is it a bad wine? Well, we're able to use all these other different functions that are not linear to separate our data. What you're up to for... Oh yeah, believe me, if you've never seen machine learning stuff before, it's, this is cutting edge crazy stuff. But if you look, I'll put here's my... If you go on GitHub, and let me see here if I can find my GitHub. I'm going to put all of this, and it's going to be heavily, heavily commented, and I'm going to put it on GitHub. And it'll be there after I make this video, probably like an hour or so after I'm done with it. So here, I'll just paste it here. So all this code along with comments is going to go, I put it in both places. It's on Twitch and also on YouTube. Yes. Yes, there's a lot of stuff to learn, but if you go through there and you play around with it a little bit, I'm telling you, if you run 10 models, you will completely understand this. 10 of your own models, you'll be an expert. You'll know how to do anything. Okay, so what I want to do now is plot to find this learning rate. And I did that before, so there's no point in going and copying all that code. I can just go and copy and paste. So here it is. So we're going to grab this, copy, and am I going to do anything else with this? Let's go get this and come down inside of here. Make sure I go to the right place. And I just called this history. That was a mistake. I should have called it history LR. So that I could separate it out, but I didn't, so that's what we got. Okay, so this is going to be history instead of history LR, but I don't want to rerun and create the model again, so I'm just going to do this, and I think everything else should work for that, and it didn't. So X and Y must have first dimension, but have shapes 100 and 20. All right. What are we going to do here? Oh, I know. Because I'm using 100 epochs, and this is supposed to be, or no, yeah. This is going to work out to being 40 instead of 100. No, still not right. We might, let's go. I think I kind of have to rerun this again. Let's just go off of, oh no. Okay, so what I do, I did 20. Let's go and let's run this for 40 epochs. This is the problem. Let's go and run this for 40 epochs. And let's do all that. Let's call this history LR like that. And let's rerun that. And then I'll change the other piece. This is going to take a minute to work, though, because I'm doing so many epochs. But I want to get highly accurate data. This is the first time you've had to. It's ridiculously fun. There's nothing. Okay, machine learning allows you to create something, to create like a genius, to create like an oracle that can like predict future. That's what I do. Like when I do inventory analysis, people are like, oh, inventory analysis, that sounds really boring. Well, basically, my job is, if I don't do my job the right way, this is how I explain what an inventory analyst does. If I do my job the wrong way, the businesses I work for go bankrupt. That's pretty serious. And because a very, very large number of businesses, a lot of people think every business goes bankrupt because they don't have sales. Well, that's true. But a large number of businesses go bankrupt because they have too many sales. So what an inventory analyst does is they look at all the previous sales and all the data that they can pull in from other different places. And they say, well, you create models like this, and then you say to a client, hey, this is what we expect you to sell over the next month. You should have this inventory. And this inventory isn't going to sell unless you mark it down to a deep level. You put it on sale. And if you do that, that's very often the difference between a successful business and a failed bankrupt business. So that's the sort of stuff you can do. You can predict the future, and it's ridiculously accurate, as you can see right here. So there we are, and then I changed this to history LR. Just making sure I got everything else here right. I did 40 epochs on this. Looking at all that. So yeah, it's very good. How did I come up with the number of epochs? I just guessed. That's all. I'm just trying to not require everybody to sit here and watch me calculate 100 epochs, and I know that based off the data, roughly how long it's going to take to fit all this data, and I don't want to sit here forever, and I'm sure you don't want to sit here forever watching these calculations. As we saw in the neural network playground on the TensorFlow site, very often the more epochs you run, the more accurate your data gets to a limit. Inventory analysis is extremely boring. Because, you know, I'm basically, a lot of what I deal with is, first off, I run online stores that sell kind of boring products. So I sell like plumbing equipment and things like that. So, yeah, I'm trying to do exciting things. As we build our knowledge base, we'll be able to do more exciting things as things continue. Okay, so this is 40, and I should be able to calculate this now. And if not, there we are. Okay, so here is our learning rate versus our loss, and guess what? Our ideal lowest point is, it's actually probably over in this ballpark for our learning rate. So you want to get like the ideal lowest rate and then subtract 10% from that. So it's probably in this ballpark. But the learning rate's just going to get you to your final results faster. So you can go on your own and play around with that to see how increasing the learning rate can get you to your results quicker. But to finish this off, I just want to make some predictions using my model to test it out and see how good it is. What did it say up here? It said that my accuracy was basically 86%. So that is how accurate it is in going and getting handwritten values. So you can come in also and test it by hand. So let's go and get, and what it's going to do is it's going to give you the probabilities of the handwritten note being one or another of the possible numbers. So I'm going to go, I did call this model 4, right? Let's say model 4. Let's use the, yep. Since we sat here and watched that calculate, let's go and actually use that hard work. So we'll say predict, and we'll go and get X test. And then what we can do is we can let's just pick the very first one based off of that, and you're going to see what it does. It's going to say that what number it thinks it is. So this is going to be 0, this first number, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? So that's what it is, 0 through 9. So based off of that, which number is this number more than likely? What does our model think it is? Well, it thinks it's this one. So you want to get the value that is the closest to 1, which in this circumstance would be this guy. So it thinks it's 0, 1, 2, 3, 4, 5, 6, 7. It thinks it is the number 7. Let's test it. So what I'm going to do is I'm going to go and get label names, which were just a list of all of the possible labels, which are the numbers 0 through 9. So I'm going to go label names, and TF dot, it's argmax. Yeah, I want to get the largest number inside of here, closest to 1. So I'll say TF argmax, and then throw inside of here Y probability and that specific value. So let's go get it. Oops, what did I do wrong? It's, I thought I had label names inside of here. Argmax. Oh, I just put that in there. There we are. So it thinks it's 7. So let's go and get the actual value and see if our model is indeed correct. So we'll go y-test and 0. And the actual result is 7. Okay? And you can see that there was somewhat of a likelihood that it could be a 9 and also a likelihood that it could be a 4. So, and you can think a 9 and a 4 are somewhat similar to a 7, but pretty resoundingly it believes it is a 7, as you can see. So that is what it does. It does these probability guesses. Let's go and pick another one. So if we throw 10 inside of here, is our model right in this circumstance? We can run it. It thinks it's a 0, and it's a 0. Okay? So there you go. There is an example of both binary as well as multi-class classifications. And you have any other questions for me? Other than that, I am probably going to call it quits. And what I'm going to do for the next video is I'm going to talk about convolutional neural networks. It's just kind of a convolutional neural network, but I'm really going to focus in on image recognition and image classification. I'm going to talk about recommender systems. And what they do is they make predictions or recommendations based off of user interactions. So, for example, the advertisements you see, they try to give you advertisements based off of that. I'm going to cover image segmentation, which is going to break images into multiple other image segments. So if you have a photograph and it goes in and automatically labels what all the individual things are in the photograph. I'm going to talk about natural language processing. I'm not sure how much of this I'm going to cover on June 1st, but I'm going to get into a lot of this. Time series analysis. I made a long series on time series analysis, but basically what it does is it analyzes data that's taken at equally spaced points in time in order to basically extract different statistics about them and object detection and all that stuff. So that's what's coming up June 1st. And thank you to everybody that joined me today. If you don't have any other questions, then I guess I will see you on June 1st. Any other questions? Thank you for stopping by. I really appreciate it. Anything? Nope. Okay, then. Please leave any questions or comments that you may have down below. And otherwise, I'll catch you next time.